Let us now discuss the AC transients of first order circuits, that means RL or RC circuits. Alright. So let us consider an RL circuit. There is a switch here, and here you have resistance and inductor. You can take R and L here. Okay. Now this switch, you can take it to be closing at t is equal to 0. And this voltage you can take as V of t. The current flowing as soon as the switch is closed, we can take it to be I of t. Here we will take the voltage V of t is equal to Vm sin omega t plus theta. Okay, theta is the initial phase, and remember we are taking the sine function here. Okay. Now if you write the KVL, then what will you get? V of t is equal to R I of t plus L di by dt. Okay. So here you can use the Laplace equation as well as normal differential equation. We will do by the differential equation method. The Laplace transform method, it will become a little lengthy, confusing. Okay. So the differential equation method, what will be, you will get a complementary function and a particular integral. This is from mathematics, but don't worry even if you don't remember. This complementary function you will get as the response because of the initial conditions. So that means you will equate input to 0 and you will solve the differential equation to get the complementary function. And the particular integral will be due to the input. Okay, and this you can get by steady state analysis. So first we will find the complementary function. Complementary function, or it is also called as the transient response, because it is not due to the input, it is only due to the initial conditions. So it will die with time. Whereas the particular integral will be due to the input, so it will remain. So it is called as the steady state response. Okay. So how to find the complementary function or the transient response? By equating the input to 0. So in that sense, what will you get? The equation is going to be LD plus R into I of t is equal to 0. Here d is equal to d by dt, right? So now this is called as the complementary equation. This will give you d is equal to minus R by L. Now the output I of t is going to be an arbitrary constant into e to the power this root whatever is there, that power into t. Okay, so that means minus R by L into t. So this is the complementary function. What about the particular integral? This is the steady state response which you can get from the phasor analysis. Okay, so we know that I bar, the current, is going to be V bar by Z. Now V bar is, the maximum value is Vm, and initial angle is given as theta divided by Z. You can write as mod Z angle phi. So you are going to get what? Vm by mod Z angle theta minus phi. Here theta is the initial phase of voltage, source voltage, and phi is the phase of the impedance. So that means what? Tan inverse omega L by R. Now the actual output will be the sum of this complementary function and P particular integral. Okay. So therefore I of t is equal to complementary function plus particular integral, which is equal to a e to the power minus RT by L plus Vm by mod Z sin omega t plus theta minus phi, right? This will be the phase, and Vm by mod Z will be the magnitude. This is the expression for current, but we have the arbitrary constant to be found out. Okay. At t is equal to 0, the current is equal to 0 because current in inductor cannot change abruptly. right? Before the switch is closed, the current was 0. So right after the switch is closed also, current will be 0. Okay. So if you equate I of t is equal to 0, then you're going to get a e to the power, this is going to be 0. So you can simply write 1 here, a into 1. So this will be equal to minus Vm by mod z sine theta minus phi. Okay. So that's how you're going to get the final expression of current. I of t is equal to minus Vm by mod z sine theta minus phi e to the power minus RT by L plus Vm by mod z sine omega t plus theta minus phi. This is the final expression for current. So what did we do? Let us just recap, because it is lengthy, it might seem difficult. First you wrote the KVL equation, and since it is a differential equation, we found out the complementary function. First the complementary function, right, and then the particular integral. This is the particular integral we found from phasor analysis. Complementary function we found from differential equations. Okay. So now I of t will be equal to the complementary function plus the particular integral. What is left to find out? This arbitrary constant. For that we took the initial condition. From initial condition we found out the arbitrary constant. Okay. So that is how we ended up with the final expression for the current in the AC RL circuit. Till now we have not talked about the transients. Now we will talk about the transient. How to get a transient free response. We saw that this was the transient response and the second part was the steady state response. As time varies, this is an exponential function. This whole part is constant. As time varies, this exponential part varies, right? So this exponential part will decay. It is a decaying exponential. And what about this? Here sine omega t plus theta minus phi. So as t varies, then it is a oscillating quantity. So that is why it is a steady state value and this is the transient value. Now what do we want? How to get a transient free response? So that means this should be equal to 0. If that should be equal to 0, this term cannot become 0. At t is equal to 0, this will be simply 1. Then this cannot be 0, Vm by z. The only thing which can be 0 is sine theta minus phi. And when will sine theta minus phi be 0? When theta is equal to phi. Okay. For transient part to be equal to 0, sine theta minus phi is equal to 0. This means that theta should be equal to phi. What is theta? Theta is the initial phase of the voltage source, right? So the initial phase of the voltage source, if it is equal to the impedance angle. What is the impedance angle? Tan inverse omega L by R. So under this condition, you will be getting a transient free response. Here one important thing that you need to remember is, what is the function that we took? The voltage source was Vm sine omega t plus theta. If the function was cos, it would have been, this condition would be changing. So how will it change? If V of t is equal to Vm cos omega t plus theta, then the current, you can do the same procedure. The final expression I will write. So what will it be? Minus Vm by z will remain as it is. Here instead of sine, you will get cos theta minus phi e to the power minus RT by L plus Vm by mod z cos omega t plus theta minus phi. That is the only difference. Wherever there is sine, in place of sine, you are going to get cos. So for this part to be 0, for the transient part to be 0, what you are going to get? Cos theta minus phi is equal to 0. For transient free response, or transient part is equal to 0. So then what will you get? Theta minus phi is equal to pi by 2. So that means theta is equal to pi by 2 plus phi. Phi you can write as tan inverse omega L by R. This is what it is, the initial phase of the voltage source. Okay. Now, here we have closed the switch at t is equal to 0. What will happen if switch is closed at some other time not equal to 0? Then what will become to the expressions? So we will take a time t is equal to t naught. For the first case, when v of t is equal to Vm sine omega t plus theta. Here the transient part of I of t will be minus Vm by mod z sine omega t naught plus theta minus phi and e to the power minus r t minus t naught by L. Okay. So in the same procedure, whatever we have discussed initially, in the same procedure if you do, you will get this result. Okay. Now here what is going to happen? For the transient part to be 0, for transient part to be 0, what will be the condition? Sine omega t naught plus theta minus phi is equal to 0. That means omega t naught is equal to phi minus theta. So that means omega t naught is equal to tan inverse omega L by R minus theta. This is the condition. So here you can see that omega t naught should be of a certain value. Okay. So if the switch is closed at t naught value such that t naught is equal to this value, then you will not have any transient. So in the previous case, the condition was on the initial phase angle. That phase angle should be like that. Then there will be no transient response. Here it is depending on the time at which the switch is being closed. Okay. Now what about the other case? V of t is equal to Vm cos omega t plus theta. In this case, the condition, I'll write the final condition, omega t naught will be equal to tan inverse omega L by R minus theta plus pi by 2. So this is the condition for cos function when switch is being closed at t is equal to t naught. So you can write a summary here all at one place. Condition for transient free response. So we have discussed various cases for the RL circuit. Right. So what was the first thing that we saw? When the source voltage was equal to Vm sine omega t plus theta. Then the condition was that the initial phase angle theta should be equal to tan inverse omega L by R. And when V of t is equal to Vm cos omega t plus theta, then what will be theta? Tan inverse omega L by R plus pi by 2. And what was the other thing? When switch is closed at t is equal to t naught. In this case, when V of t is equal to Vm sine omega t plus theta, then the condition is omega t naught is equal to tan inverse omega L by R minus theta. And when it is a cos function, Vm cos omega t plus theta, then omega t naught should be equal to the same angle will repeat, just you have to add plus pi by 2. This is for the RL circuit. Now what will it be for the RC circuit? The procedure for derivation will be the same and the results are also somewhat similar with only slight differences. Okay. So if the source is having a sine function, then theta is equal to tan inverse omega RC. In the previous case, in the RL case, it was omega L by R. Okay. Omega L by R you can write as XL by R. Omega RC is what? This is given by R by XC, because XC is 1 by omega C, right? So just inverse is happening. Here in RL circuit it is reactance by resistance, and in RC circuit it is resistance by reactance. This is just for the sake of remembering, for easily remembering I am telling you this. Okay. So what if there is a cos function? If the source is having a cos function, then theta is equal to the same angle plus pi by 2. And what about when switch is closed at t0 and the function is sine? In this case, omega t0 is equal to tan inverse omega RC minus theta, right? It was in the same in the previous case, RL case. And what if it is t0 and cos? Then omega t0 is equal to the same angle tan inverse omega RC minus theta plus pi by